Okay, so we're going to continue on with our discussion of the biosynthesis of amino acids. I'm just going to continue to pick on ones that are interesting and things that we hadn't incidentally touched on during like the catabolism lectures and that sort of thing. And so the next one up is isoleucine. Isoleucine is a really interesting amino acid because it has a second stereocenter in this methyl group at the beta position. And so introducing that methyl group is very interesting. I think it's a great reaction. So let's get into it. So we're first going to take pyruvate. We're going to react it with TPP, which is this thiamine diphosphate. And we're going to actually lose CO2 and convert that pyruvate into basically an acetyl group hooked up to the TPP cofactor. So let me draw the TPP cofactor really quick. So we have CH3, and we've got some stuff here and some stuff here. Okay, when this hooks up to the pyruvate, and the pyruvate is able to lose CO2, we get this structure, and this structure is actually nucleophilic. We've talked about this before, but it's actually nucleophilic at what was the carbonyl carbon, which is what makes TPP quite remarkable. And we're going to react that with alpha ketobutyrate by way of an aldol reaction. Okay, so the alpha ketobutyrate has the ethyl group built into it. And the way this aldol reaction works is we are going to basically push electrons out here. Now, when we do that, we also simultaneously, well, I can push the arrows a little bit. That's fine. So when we do that, we have our cofactor now. Now, the reason why we push those electrons is after the nitrogen moves the electrons over, yes, it becomes positively charged. Yes, it becomes positively charged, but it's also now aromatic. So we're going to have an O minus here. We have an ethyl group down there, CO2 minus. Okay. We probably pick up a hydrogen during that addition, but let's just do this. 1, 2, 3, 4, 5. Oh, this isn't a bad reaction. Probably doesn't happen this way. It's probably facilitated, but we're going to transfer the hydrogen, come down, and then actually kick off this aromatic ring as a leaving group. Now, why would we do that? Well, we actually regenerate our catalytic cofactor, the TPP cofactor. Which looks like this. So we have a plus on nitrogen, but after we lose that group, after we break that carbon-carbon bond by reforming the carbonyl, we actually get back an aromatic molecule. This is equivalent to, if I just draw that carbon between the nitrogen and the sulfur, that is the equivalent of a carbene. And that's what we get is, I guess I'm drawing all of it. Oop, nothing there. Okay, anyway, this is TPP right here. So we've talked about thiamine diphosphate before. It's a super cool catalytic cofactor because it can convert aldehydes into nucleophiles at the carbonyl position. And this was related to that Rovis chemistry that we talked about earlier in the semester. Okay, so what are we going to do with this molecule? It's starting to look like our molecule of interest a little bit, but not quite. Well, what we have to do at this point is we're going to react this with an enzyme that uses the magnesium 2+ cofactor. We're going to build this complex where the carboxylate oxygen and the keto oxygen coordinate to the magnesium +2 center. And then we've got an OH. And the book doesn't specify stereochemistry here. I would guess that the TPP reaction is stereospecific. But here's what we're going to do. Super cool reaction. So base is going to deprotonate the OH and push the electrons down and then kick the ethyl group over. And then let's go ahead and just, because we're in biochemistry land, we'll just pick up a hydrogen from somewhere. Okay. When we do that, we get to this molecule, where the ethyl group has migrated. Get migration of an ethyl group. I think this is an amazing transformation because this is difficult to do chemically. So we really have to rely on an enzyme active site to push that ethyl group over. And it's all facilitated by the magnesium activating the carbonyl to make it more electrophilic at the same time that the base is positioned to do the deprotonation. So super cool transformation. I would be interested to know if there's any biocatalytic applications of this. Outside of like the cell and that sort of thing. Obviously, making isoleucine is important. Okay, now at this stage, we're going to do a reduction of the keto. It says here we have NADH, H plus, sure, NAD plus. So we're going to reduce the keto to the alcohol. And at this point, we have now introduced a new hydrogen. I'm going to highlight that hydrogen and couple it to the, if we wanted to highlight all the hydrogens, we could. But let's focus on this red hydrogen. Okay, now this red hydrogen is alpha to a carboxylate center. So we could conceivably think about a base coming in and grabbing it, pushing the electrons down to force a dehydration, particularly if an acidic hydrogen is positioned close by, or even hydrogen bonding to the OH at the beta position. Okay, when we do that, why would we want to do that? Well, we get this species, which can tautomerize. It's a detail that I missed, but this will tautomerize into the, let me draw it with the same orientation so that we don't all just get lost here. All right. If we tautomerize this, we get CO2 minus at this stage. We have an alpha keto acid, which we can then do a PLP dependent transamination to generate the alpha amino stereocenter. Now, one thing I want to look really quick that I missed in my initial reading was, well, they don't discuss it. I'm interested in how that stereocenter forms. I'm not sure how this stereocenter is set by the enzyme. And it's not in the book. Like during the tautomerization, do we see it being set? During the transamination, do we see it being set? I think that's an interesting detail. Perhaps we could envision a type of dynamic kinetic resolution, like we talked about in the paper, of the alpha keto acid through a transaminase, which then sets that stereocenter. Or maybe during the tautomerization, we see the enzyme selectively want to form one tautomer over the other. Okay, so there's there's L-isoleucine. The S stereocenter at the amine position comes from just our PLP dependent transamination reaction. Okay, so if we want to make valine, we can do pretty much the same reaction, except we don't have to worry about that second stereocenter. So valine, we're going to proceed with the same early reaction where we have our TPP cofactor. So I believe this is R prime, CH3R. Okay, and this time I'm going to do the biochemistry shortcut, where I'm going to let this come down and do the, well, no, it doesn't work that way. It has to be that lone pair. Okay, well, it is what it is. All right, in this previously we used, we had an ethyl group at the end of an alpha keto acid, and the ethyl group went along for the ride to give us isoleucine. So here we just have a methyl group. So it's sort of the same pathway where we're next going to form a beta keto carboxylic acid with an OH at the alpha position, and this time a methyl group instead of an ethyl group. And then what we're going to do is see the methyl group walk. Now, methyl groups walking, that's not that big of a deal compared to an ethyl group. So ethyl group, all of a sudden, that's it. These hydrogen or these atom shifts where you walk a group next door, it's called a 1-2 shift. And I'm going to clean up this OH deprotonation. These are really difficult things to have happen. You really don't see them happening unless you're doing a hydrogen shift or if you're doing a methyl shift. But ethyl shifts are unusual. Phenyl shifts can actually work because the phenyl group is just kind of special in that respect. It can kind of go through some different mechanisms to get there. But ethyl group is just so bizarre. So anyway, we do the methyl shift now. And that's going to give, and we'll pick up an H plus while we're over here. This species, which we can then engage NADH and an acid, not a catalytic cofactor, so we need to deal with NAD plus at the end of all of this. That's going to give an OH, which can then do a dehydration. And tautomerization. To get this, which can then undergo a transamination reaction to generate the alpha stereocenter. And we are at valine. Okay, so we flew through that one, but that was because it was quite similar. Okay. So next, kind of keeping with this string of amino acid types, let's go into the biosynthesis of leucine. So the biosynthesis of leucine looks like this. Okay, we're going to actually use an intermediate from the valine pathway, which was the precursor in valine just prior to the transamination reaction. So we have the isopropyl group on the carbonyl. You can see that it's the same as what's up here. Okay. So we have those, we have made that through that pathway. Now we're going to do an aldol reaction with acetyl-CoA, and I'm just going to take a shortcut to writing this. I'm just going to put a little negative charge in here. I'm going to let the negative charge do the attacking. Just want to make sure, yep, that's how it goes. So we're going to do that. Which gives us, I'm going to draw the OH here. Here I'm going to put the carboxylate. Now, things look a little bit different with this. So we're going to draw the new bond with a little bit bigger of an indicator so we know what we're working with here. Okay, and then we have this thioester intermediate that doesn't stick around too long. That's immediately hydrolyzed to the carboxylate. Okay, so once we're at the carboxylate, it looks like we have a hydroxyl group migration, which is kind of interesting. Let me get to that dicarboxylate. Okay, so it says we're going to do a dehydration, rehydration. So that means we're going to lose water. This isn't shown in the book, but it's not like overly complicated. Oh, I just lost that OH, didn't I? Sorry. This kind of looks like fumarate. We're going to add water to it, but this time the H2O is going to add to this position. And then we could push electrons through to pick up an H+. So we're going to just flip spots, the H and the OH, dehydration, rehydration mechanism. Enzymes tell us what they need, and we will position things accordingly. Okay. Now that we've got that position oxidized, we can start to think about ways to introduce the amine group. And so what we're going to do is an oxidation at the alcohol position, alpha to that right-hand carboxylate, to make a ketone. And then once we're at the ketone stage, I'm going to redraw this lower carboxylate so that it looks a little bit more decarboxylate-y. That is, we can take the negative charge and push electrons through. So having that ketone and that ketone oxidation state enables efficient decarboxylation. And we can reprotonate. And maybe you've gotten comfortable enough to see an alpha keto acid and know that if we have our entire desired amino acid, which in this case was leucine, which has an isobutyl group or an isopropyl group downstream a little bit, we know that we can get here. Okay, so all we have to do is transamination at this point. And amino acid's upside down, so it's a dash. But there's now leucine instead of isoleucine. Okay, so there is a cool pathway discussed on page 314 of the book. I'm not going to go through it. I'm going to go through the fun part of it, but we are going to kind of skip over. So I'm just going to invite you check out the chorusmate pathway. So the chorusmate biosynthesis looks like this. We're going to take this species with a wedge here. That's going to go to an enol ether carboxylate. Oh, excuse me. We're going to have an OH as a dash. Okay, so there's chorusmate. And chorusmate's an important precursor to the biosynthesis of several of the aromatic amino acids. So chorusmate can make tryptophan. And so the way this works is we are going to see, I want to see this pathway with some detail. Okay. So we're going to talk about how we can use this en route to tryptophan, excuse me. En route to tryptophan. So we've talked about the tryptophan biosynthesis during the journal clubs, but if we start with chorusmate, I'm going to draw it in a rotated form just to match the book. Definitely don't want to get lost here. Okay. What we're going to do is first make a molecule called anthranilic acid, or anthranilate, if you've got that zwitterionic deprotonated form. So here the ammonia is going to add to this double bond. We're going to push electrons through and then push off this OH. And the book says this is going to be coordinated to a magnesium to activate that loss of OH. Now at this point, we will have the molecule. Stereochemistry is not described here. It's okay. So we have this weird molecule that's actually happy enough just to leave. So this H could leave to reestablish an aromaticity. And we could go here and, I wonder if this negative charge that results at this at the end of that alkene could pick up the hydrogen. It's kind of interesting. The book suggests not. I believe it if it wasn't. In an enzyme site, we can provide hydrogens as needed, but we're careful. We usually don't rely on kind of an intramolecular reaction happening to make sure the reaction's efficient. Anyway, we get to this cool molecule. Gosh, I really like this molecule. As many of you probably know, I like benzene. It's a fun molecule to study. So I'm just going to mention an aside here. I've always wanted to do this reaction, but been super scared because it's a little dangerous. But what you can do is you can take anthranilate and convert it into a diazo salt. So this is, let me write that normally, where you have N2 plus. Then with N2 plus, this negative charge can kind of push through the carboxylate and kick off N2 because N2 is a fabulous leaving group to give us benzene. Now, unfortunately, you produce CO2. Sorry to be short on the decarboxylation arrows. You produce CO2 and N2. So it's quite likely that this reaction will explode if it's held under pressure. So not the safest set of conditions, but my goodness, is this a green way to make benzene? I mean, CO2 and N2 being your only byproducts, that's wonderful compared to the current methodologies. Well, I guess when I was in grad school, I got to be part of a team that had a methodology that had no byproducts in the benzene formation. So that one's probably the champion. Okay, that was a good team I was on. Okay, so anyway, let's get back to tryptophan. Okay, so back to tryptophan now. So with anthranilate, excuse me, anthranilate, we can go through a few steps. We can go through a few steps that involve sugar condensation. I'm just going to write sugar phosphate here, because I don't always have the energy to draw all of the sugar intermediates. So I'll draw one. Maybe you all disagree. With your youthful vigor, Haworth's projections don't bother you as much. Okay, so we have this kind of this fructo, this kind of furanose sugar. Some OHs down here. And that's what the book says we have. So that's going to ring open. Yeah, I mean, I see where the carbonyl needs to form. So I guess we just draw this with a question mark. Huh, okay. I don't see that transformation, but let's go ahead and just draw the resulting product. It's probably obvious to people with more sleep under their belt and that aren't actively recording. So sorry about that if this just bothered you, but let's just jump to here because this will take us home. So we're at this stage, and what we can do is we will decarboxylate and do an aldol, like a Friedel-Crafts like condensation at the alpha position. You know, the book kind of abbreviates this too. We're going to connect here to here and we're going to lose CO2 and H2O. Okay. So now we have this molecule where we've got some sugar stuff. Okay. So at this point, this is called indole 3 glycerol phosphate. So hopefully you can kind of see the glycerol, that 3 carbon, 3 carbon, 1, 2, 3 carbons of glycerol. There's indole, which is benzene fused to a pyrrole, and then the phosphate. And so this is actually what engages now the tryptophan. The tryp synthase is what it's called, tryptophan synthase enzyme, where it first reacts with tryp-A, which is one of the subunits of the enzyme. So it's one of the proteins that's bound together in this enzyme, where the glycerol 3 phosphate is removed, providing indole. And then indole reacts with serine to make tryptophan. That's a pretty cool reaction. Okay, now the way that works is actually an organic 2-like reaction. It's an electrophilic aromatic substitution reaction, where what happens first is we could look at each of these mechanisms separately if we want to, but let's just stick with TRPB. TRPB is the kind of the meaty one. We can actually buy indole. That's not a big deal. What we're going to do is take serine and react it with PLP in the TRPB active site. Now we've activated the alpha position, alpha 2, the carboxylate, and it's activated in particular towards all of these reactions, dehydration, decarboxylation, that sort of thing. And what we're actually going to do is, okay, we're on that side of the molecule. So we're actually going to do a dehydration reaction. To lose water and form an electrophilic intermediate and this is PLP plus in this case, in this form. We have an electrophilic intermediate, which is going to react with a good nucleophile. In this case, we're going to pick on indole, which is nucleophilic. Draw arrows to show this at the 3 position. That's the book. I mean, I love this book, but it's getting a little short on the curly arrows at this point in the game. That's okay. They've taken us pretty far. It's nice to go all the way. So, okay. All right, so now at this stage, I'm not really for sure what happens next, but what we need to do is lose a hydrogen to reestablish aromaticity. That's kind of a key point in the electrophilic aromatic substitution reaction. And additionally, the PLP lone pairs need to push through and protonate the alpha position. It's going to reestablish aromaticity on the indole. That's going to after we do a transamination where a lysine residue swings and picks up the PLP to make a new shift base, we'll release the NH2 again. There's our carboxylate, and there is our tryptophan amino acid. Okay, so moving on, we will now do L-tyrosine and phenylalanine. Okay, now to do these, we need to actually pick up with chorusmate. So chorusmate is a direct precursor to phenylalanine. So if I draw this again, this was the 6-membered ring, some double bonds, a carboxylate, and this wonky kind of enol ether carboxylate. So some weird stuff was going on here. Okay, now what we're going to do, love this reaction, fan favorite, we're going to do a 3,3 sigmatropic rearrangement. Gasp, right? Gasp. This is great. So this is a 3,3 sigmatropic rearrangement. And this would be an example of the Claisen rearrangement based on the position of the oxygen. So this transformation brought to you by the element O, right? I just heard somebody say that at a meeting, and I thought it was brilliant. So I didn't come up with that. That would be all Lydia. Okay. So we're at this stage now. After that Claisen rearrangement, the OH in this position. All right. I guess I need to draw my carboxylate out. Sorry, I try to pay attention to when I need to do that, but it's just so much easier for the most part just not to. Okay. Now we're going to decarboxylate, push through, and then push off the OH, and that gives us the alpha keto acid precursor, just one transamination away from phenylalanine. Transamination. To our amino acid. Okay. This is great stuff because we do the 3,3 sigmatropic rearrangement, the Claisen rearrangement, to form the carbon-carbon double bond and really set ourselves up to aromatize after we lose water and lose CO2. We've got our aromatic ring, then just another one of these other just transaminations. These enzymes are just sitting around waiting to pick off alpha keto acids and turn them into something useful. Okay, so this molecule along the way, after we did our Claisen rearrangement, is called a prephenate. Down below, that's phenylpyruvate. Let's not worry about that right now. So let's use prephenate again to get to L-tyrosine. We'll call it a lecture. Okay, so we're going to use prephenate again. Prephenate again. And so at this point, what we're going to do is instead of decarboxylating and losing the OH, we're first going to intercept this intermediate with an oxidation reaction, so busting out our NAD+, to oxidize this to a carbonyl para to the CO2 minus. Draw that. Got to make that carboxylate ready for decarboxylation. Okay. And CH2. It looks like in my previous step I added a CH2. Didn't I? Yeah. Okay, good enough. All right, so now we're going to go decarboxylation again, except we're going to push the electrons up and into the carbonyl, and we can just let them pick up a hydrogen atom. And that's going to give us the alpha keto acid precursor to tyrosine. So forgive me, I'm going to save my virtual paper for the next lecture. We do a transamination reaction here to generate the amino acid. And we're back. Okay, so a lot of kind of setting up some chemistry to get to a really cool alpha keto acid so that we can do the transamination to set the amino stereocenter. It's just kind of remarkable the chemistry that nature takes advantage of to get to these amino acids. So, looking ahead, I felt like these all kind of connected well enough together. Maybe the tryptophan was a little out there, but it got us sort of started on phenylalanine and tyrosine. The other one I didn't get to was in the book was histidine, super cool, another aromatic amino acid. These are really fun to make, but it was a little bit like different from what we had been talking about. So it just would have been a brand new mechanistic path. So, okay, we'll call it here. We'll call this one in a lecture. So we'll see you next time, I guess.